Hello everyone, welcome back to CSE 545 Software Security. In this video, we will talk about the IVE binary and we will talk about dynamic linking for ELF binary. So you may wonder that how programs manage to call library calls, for example, libc functions. And in this video, I will show you how a program managed to call C library calls. And especially, we're going to using a running example as such, and I'm going to show you how a program like this managed to locate library functions such as put and execute it. So first, let's look at this program together. This program is very simple. It has only one function called main, and in this function, it is going to call function put for twice. The first time, it's going to put with a string of hello world, and then the second time, it's going to call put with the string of this is CSE 545. And as we already know, put is a function coming from glibc. And now we're going to run this example in a Linux operating system and look at how the program executes by looking at the instructions. So in the source code, again, it calls function put for twice. Now let's compile it. And for the ease of demonstration, I'm going to compile it as a non-PIE, non-PI binary. And also I'm going to enable debugging symbols just in case that we need it. Okay, after that, I'm going to show on one side the disassembly of the code using opsdom. And then on the other side, I'm going to use GDB to dynamically run it. And I'm going to set a breakpoint at main so that the program will stop when it starts to execute it. All right, so I'm going to start. And now we're stopping at instruction, actually the statement before calling puts hello world. And as you see on the screen, actually, let me go to the static view. So here we are before calling puts function. And then now let's gonna execute this instruction by instruction. So next, now we're at for F2 is over here, right? And then for F2, let's look at the disassembly. It's a call instruction. All right, and now we're gonna do step. Here, that means that we're not gonna just like execute the instruction right after for FV, which is 503. We also call it a fall through, but instead we're gonna go into the call instruction. So now if we do step I, or you can just use SI, which is short for step I, you'll be able to go to instruction that this call instruction points to, which is 4003F0. So you see over here that we are trying to call function puts coming from the C library. And instead of actually going into the C library, now we're going to go to a place called put, and then it said this is like put at PLT. So what is PLT? Let's take a look together. Okay, now we're going to do step I. So now here we are, 4003F0. And on the right-hand side, let's also go to the disassembly at that particular instruction. So it is 4003F0. Okay, it's right over here, and you see that this instruction, what it does is a jump. Okay, and now I'm going to use this upper panel to record what we have go to. So remember that at the beginning, we have call, and then that's put at PLT. And now we are at 4003F0, which is put at PLT. This is 4003F0. And let's see what's going to happen. So here, we found that actually it's going to continue to jump. And this instruction, jump Q star with the offset of RIP, it means that it's going to jump to a location. And then this location stores at the place with the offset of this particular value to the current RIP. So we know what is the value of the current RIP. At this point, it's 4003F0, right? Because RIP stands for the instruction pointer. So what we need to do is to add this number 4003F0, and of course this is in hex, add that with hex 200 through C22. So the total of this two number is 601018. So Optimum has already helped us calculate it. So now let's look at the content stored in that particular location, which is hex 601018. 60188. And we know that since it is a function pointer or say an instruction pointer, we need to do G instead of to get the entire 64-bit information. And in this case, we see that the location that this hex 601018 points to is 4003F6. And this is actually right next to put at PLT. It's over here. Okay, so now we know that actually throughout this location 601018, now we're gonna actually jump to the next instruction of 3F0. So we know that right now this location stores the value of 4003F6. And now we're gonna go to the next instruction, which is a push Q and then a jump to again another location. And pay attention that right now there's no star over here, so it's gonna jump to this location directly instead of jump to the location that stores at this particular address. So here we should just go to 4003E0 directly. So the next instruction after 4003FB should be 4003EE. And let's run this together. So now let's do next I. We're at 3F6, right? And then we're going to continue. And here now we're at 3FB. You can see the instruction over here. Okay, and now we're going to do next I again. Now we jump to 4003E0. And let's take a look at 403E0, what it's saying over there. Okay, so here is 4003E0. And we found that what it does is to do push statement. And after that, it's going to jump again. And in this case, it's going to jump to the location that is stored in 601010. And let's take a look at what is stored in 6100. So it's 601010. And now we get a new address. And I'm going to take it down. So after 4003E0, we're going to jump to it's going to jump to the location stores at 601010. And now in this case, that value is this 7FFFF and then 7DEC 780. All right, next we're going to continue and see what's going on over there. And now we're at 7FF, 7DEC, 780, that location. And we see that actually that is the start of function DL runtime resolve. So actually, so what this function does is that it will read the symbol of put and try to figure out the address of put, and then it's going to store the address of put into the location that originally over here should store the address of put. So we're not going to go through this, this function instruction by instruction, but let's just like execute it very quickly. So actually this function called BL fixup, and what BL fixup does is that it will find the location of put and return that location as the return value of this function. And also it's going to store the location, store the location of put into this place, which is 601018. And now if you look at 6018, we found that it is no longer 4003F6. So now it is update to the the new place. And let's take a look at this place. Let's actually try to output some instructions. That's actually the start of IO puts. This is the location of put, the function that we want, from libc. So now you see that throughout this entire program will be able to find the address of put, and then it's gonna save that address into somewhere that our own original program will be able to locate, so that next time when function put is called again, it will no longer need to go through this entire process again. And this location, which stores the address of put, is called GOT. That is global offset table. And here, this location is called PLT, stored in PLT session. This is like the trampoline that will help us to jump to the actual location of function put, even though program does not know the location of put ahead of time. And now let's go back to the slides and go over this process again. So suppose that we have this function main, and function main calls put for twice. The first time when the program calls put, or first go to the PLT session, it will call put at PLT, and then the instruction in the PLT session will direct the execution to jump to the location that is stored in the GOT table, the global offset table. And after that, at the first time, the global offset table stores the next instruction of puts at PLT. So in this case, it will jump back to the PLT session. And for that, the PLT session will continue execute to jump to DL runtime resolve. And after calling DL runtime resolve, the location of put will be stored into the GOT table, and DL runtime resolve will jump to the actual function, which is put. And this is for the first time that we call function put. Because we already update the information in the GOT table, so next time when we call put again, although put will go to PLT session again, PLT will actually get the actual value of puts directly from the GOT table, so it's already stored over there. And now the program will directly jump to put instead of going to the previous like DL resolve all over again. And this is how dynamic library works. So you may wonder why I am talking about this and how is this related to software security? Well, apparently, dynamic linking has security concerns. Since dynamic linking takes advantage of GOT table, which is a table full of function pointers. So if someone is able to overwrite those function pointers and change that to a malicious function, then if the program is going to continue executing, like calling put again, then it will actually execute the malicious function that we put into the GOT entry. And second is that using the GOT entry, we will be able to leak address of a function pointer, such as the function pointer of those that are stored in the GOT entry, since they're already over there. And the reason why we cared about this is because sometimes we need to know the base address of libc so that we can enforce an attack such as ROP. If you still remember, in last week, when we do this in-class lab, I was giving you the base address of libc. However, given the fact that libc function's function pointer will be stored in a GOT table, we could use ROP, or we could use other way to actually leak that function pointer out so that we will be able to get the base address of libc, given the fact that libc's function doesn't change their relative offset to the base address, although the base address of libc may change. So in this way, we will be able to know the base address of libc, and from then on, we'll be able to use the ROP chain, because now we know the offset of the ROP gadget, and now we also know the base address of libc. So after we use ROP gadget, whatever ROP gadget finding tool, to find those ROP, we'll be able to add, the offset of ROP gadget with the base address of libc, and we'll be able to get the actual address of those ROP gadget in a running process. You may feel confused about what I just say, but that's okay. In our next video, I will show you how to leak the base address of libc so that you can use that and then connect that with the attack that we mentioned in last times in class lab, and you will have a complete attack